Out there in space, some stars don't shine alone, they cling tightly to a nearby companion, and it's not by accident. Little by little, they start pulling matter from the star next to them, almost like they're draining its life away. It's a real process, observed by scientists, and it happens quietly, but with powerful consequences. These stars are known as vampire stars, and as strange as that may sound, they're part of a cosmic dance that can end in massive explosions, or in the slow, silent death of a star. The name might sound like something out of science fiction, but vampire stars are very real and surprisingly efficient. They don't have fangs, and they don't swoop down from the sky at night. Instead, they exist in a very specific setup known as a binary star system, where two stars orbit around each other, locked in a constant gravitational dance. But sometimes, that partnership becomes dangerously unbalanced. One of the stars starts to grow, expands past its limit, and loses some of its outer layers. That's when the other star begins to feed. The one doing the feeding is usually much denser, often a white dwarf, a neutron star, or even a black hole. These are dead or collapsed stars, extremely compact objects that no longer burn like regular stars, but still have incredibly strong gravity. That gravity pulls the outer gas layers from the neighboring star, stripping it bit by bit. This process is what gave rise to the name vampire star. The denser star feeds off the lighter one, drawing in hydrogen and helium like a slow, cosmic siphon. This stolen material doesn't fall straight into the dense object. Instead, it spirals around it, forming what scientists call an accretion disk, a swirling, superheated ring of gas that glows with energy, especially in the form of X-rays. It's through these powerful emissions that astronomers can detect and study these feeding stars, even from thousands of light years away. This isn't just theory. These systems have been seen and studied. A classic example is Vela X1, where a neutron star is actively pulling material from a massive blue supergiant. Another famous case is Cygnus X1, one of the first confirmed black hole candidates, where a visible star is slowly being drained by something invisible, but incredibly heavy and powerful. These examples aren't from faraway galaxies. They're right here in our own Milky Way, reminding us that these violent interactions are much more common than we once thought. What's even more fascinating is that the victim star doesn't always die right away. Some manage to survive for millions of years, even while losing mass. It's like they're stuck in a toxic relationship they can't escape. But in other cases, the end comes suddenly, when the accumulating matter triggers a huge outburst, like a nova or even a Type Ia supernova, powerful enough to completely destroy the system. And the strange twist? These explosions help astronomers measure distances across the universe, turning scenes of destruction into tools for discovery. So in the end, vampire stars are more than just a catchy name. They represent a one-sided relationship in space, where one star grows at the expense of the other. And studying them helps scientists understand how stars evolve, collapse, and even how they shape the universe itself. After all, the atoms that make up our own bodies were once formed inside stars, and some of those stars might have lived through violent, dramatic encounters like these. When we say one star is sucking matter from another, it's not an aggressive attack or a sudden event. It's a slow, steady process, driven entirely by gravity. It starts when one of the stars grows bigger and crosses something called the Rush limit. That's an invisible boundary where gravity from the companion star becomes strong enough to start pulling material away. But the stolen matter doesn't fall straight onto the dense star. Instead, it spirals around it, forming a glowing, swirling structure called an accretion disk. Inside this disk, gas spins at incredible speeds. The friction between the particles heats everything up, sometimes to millions of degrees. That heat produces intense energy, especially in the form of X-rays, which is how astronomers detect these systems from far across space. Eventually, the gas loses momentum and falls onto the vampire star. If that star is a white dwarf, the surface starts collecting this new material until something dramatic happens. The pressure becomes too much, and it triggers a nuclear explosion on the surface, a flash of light called a nova. These explosions make the star shine thousands of times brighter for days or even weeks. Sometimes, the feeding goes even further. If the white dwarf keeps gaining mass and gets too heavy, past a certain limit known as the Chandrasekhar limit, it becomes unstable and explodes completely in a Type Ia supernova. These are some of the brightest events in the universe and are used by astronomers to measure vast cosmic distances. When the vampire is a neutron star or a black hole, the effects are even more extreme. Instead of surface explosions, you can get bursts of X-rays or powerful jets of particles shooting out into space at nearly the speed of light. In the end, this entire process can last millions of years, slowly draining the life from one star to feed the other. It's not violent at first, but it's relentless. And it shows us just how intense and dramatic life among the stars can be. Vampire stars aren't just a theory. They've been seen and studied using telescopes and space-based X-ray observatories. One of the most famous examples is Cygnus X1, located about 6,000 light-years from Earth in the constellation Cygnus. It was one of the first systems to offer real evidence of a black hole. In this case, a black hole is pulling matter from a large blue star. That stolen gas forms a hot, spinning disk that lights up in X-rays, making the system visible even across great distances. Another fascinating case is Vela X1, where the vampire is a neutron star, an ultra-dense remnant of a dead star. It orbits a massive supergiant star and feeds off its outer layers. The material flows toward the neutron star and creates regular bursts of energy, especially in the X-ray range. Other binary systems like SS Cygni, RS Ophiuchi, and T Coroni Borealis show similar behavior. Some of these systems stay quiet for years, then suddenly erupt with a massive flare, like the vampire star just took a bigger bite. Astronomers watch these outbursts closely because they reveal valuable information about how stars behave under extreme conditions. These aren't distant galaxy phenomena. They happen right here in the Milky Way. Watching these systems is like watching a cosmic drama unfold in real time. It shows us that the universe isn't always peaceful. It's full of tension, gravity battles, and sometimes one-sided relationships where one star simply can't survive. In space, every action has a cost. And when a vampire star takes too much, the results can be explosive. As matter builds up on the dense star, the system becomes unstable. If the vampire is a white dwarf, the stolen material collects on its surface until it triggers a nova, a sudden nuclear explosion that dramatically increases the star's brightness for days or weeks. But if the white dwarf keeps feeding and becomes too massive, passing the Chandrasekhar limit, it can no longer hold itself together. That's when it explodes in a Type Ia supernova, a blast so bright it can outshine entire galaxies. These supernovae are incredibly useful to scientists. Their consistent brightness makes them perfect for measuring the size and scale of the universe. Now, if the vampire is a neutron star or a black hole, the effects are even more extreme. Instead of surface explosions, these objects can release powerful X-ray bursts or even shoot jets of particles into space at nearly the speed of light. What's important to understand is that the feeding process might take millions of years, but when it ends, it usually ends big. These aren't just quiet cosmic interactions. They can shape the evolution of galaxies, seed space with new elements, and give scientists insight into the most powerful forces in nature. At first glance, vampire stars might seem like a strange curiosity, but to astronomers, they're a goldmine of information. These systems let us observe extreme physics, gravity, heat, pressure, and motion on scales that we simply can't replicate on Earth. They also help us understand how stars live and die. By watching how mass transfer affects each star in the system, scientists learn how binary systems evolve, how stars influence each other's fate, and how these interactions shape the future of galaxies. Vampire stars are also connected to one of the biggest tools in astronomy, Type Ia supernovae. These explosions, which sometimes result from the feeding process, serve as standard candles, events with predictable brightness that help astronomers measure distances across the universe. In fact, this is how scientists discovered that the universe is expanding faster than we thought, work that won the Nobel Prize in Physics in 2011, and finally, these systems help detect black holes and neutron stars, objects that can't be seen directly. When one of them fades, we see the evidence in the form of X-ray emissions or gravitational effects on nearby stars. So yes, vampire stars are dramatic, but they also hold answers to some of the biggest questions in science. They're not just feeding, they're teaching us how the universe really works. In the end, vampire stars remind us that space isn't always calm or balanced. It's full of intense relationships, slow destruction, and unimaginable power. But it's in these extreme situations that science uncovers the most important clues about the universe. If you enjoyed this journey into the darker side of the cosmos, make sure to like this video, subscribe to the channel, and turn on notifications so you don't miss the next discovery. Thanks for watching, and see you next time, here on the edge of the universe.